Hey everyone, and welcome back to the Pi Pico emulator coding live stream. So, first of all, hey to Steve. I see that you are here. Great to see here. Great to see you here again. And as always, also on the Walkway Discord server. Let me share my screen and start by going over the open issues. So, what do we have for today? So there is one thing we forgot last time about the PIO. There is this thing where you can, so in the last 3 episodes we worked on the programmable I/O, PIO, and we implemented most of it. Actually, if you want, you can check it out on walkway.com. There is a bunch of projects that already use the PIO, for instance, to drive NeoPixels. So there is like cool stuff people have been doing with that. And we forgot to implement one feature, which is FIFO joining. Usually the PIO has a FIFO, a queue of 4 entries for RX and TX for each of the machines. But you can concatenate those 2 queues into a single FIFO queue, and we didn't implement that. Now, my goal for today is to actually work on the USB peripheral. So for now, we are going to skip this feature until someone either asks for it. So if somebody needs it, then just let me know here in this issue and we'll work on it. Or if somebody wants to implement it, it shouldn't be too complicated, I guess. Like we have this PIO class that we worked on, and there is like this state machine, and then there is this RX FIFO and TX FIFO. And I guess what you would need to do is just read the documentation, see which register enables this FIFO joining behavior, and instead of having those read only, just create a new FIFO. If I'm not mistaken, when you join the FIFOs, it discards its contents anyway. So whenever you are joining the FIFO, just create a new RX or TX FIFO with the new capacity. And then if you stop joining them, then just create those 4 entry FIFOs again. So I don't think it should be too complex, but I want to focus on USB today. And hi Valerio, good to see you here again as well. Welcome back. So if anyone wants to take it, then you are more than welcome. Otherwise, I'm going to wait until somebody asks for it. All right, so today we are going to start something I wanted to do for so long, which is the USB peripheral. And the reason I wanted to have USB is basically that's the default serial interface for the all the RP2040 platform. So either the Arduino Core, MicroPython, or even CircuitPython. As a matter of fact, as far as I know, with CircuitPython, the only way to go would be to use the USB peripheral. Without a USB peripheral, we can't really run CircuitPython. It needs it in order to run. So I'm not very optimistic we will get to running CircuitPython today. We still have some mileage to go before we do that. But I think having USB CDC at least, which is the serial over USB, would be very nice. And we'll try to get there today. All right, so first of all, let me assign myself to this issue. And then let me see. So let's go to the datasheet. And there is like this whole section about the USB. And oh, there is like USB made simple. What is that? Where did it open this link? Oh, it didn't. Maybe I should left click. Yeah, okay. So USB made simple co-UK. Oh, interesting. So yeah, so I'm not very familiar with the USB, so this may be useful. I guess the electrical is less interesting, but data flow or protocol could be useful. Let's keep that open for the time being. And yeah, that's the end of the USB. And So the USB has like two parts. It has a host controller and device controller. And in our case, we are just interested in the device part, because the host is when you plug other stuff into the Pi Pico, and that's not what we need for the USB serial. The USB serial is when we plug the Pico into the computer. There is like DPRAM, and I guess, yeah, it's not very interesting. I think this is all like the electrical stuff. We need okay, so it has 4K of DPSRAM, dual port SRAM. It stores the control registers and data buffer, and you can access it either DWORD, word, or byte resolution. All right. So yeah, so this is like the DPRAM. So it has 4 kilobytes, and there are registers that start at this address, but where are those addresses mapped at the RAM? It's probably written somewhere. So there is this endpoint control register, right? Buffer control register, device controller. Yeah, device is the interesting part. So yeah, this is like, seems like kind of state machine that describes or a description of how the RX and TX state machine work. The host controller is not interesting right now because we want to work on the device. Okay, programmer module. There is a standalone USB device example. We may need that because usually they use a library called TinyUSB that takes care of everything of the protocol, and I guess we would need to implement at least some of the protocol in order to be able to enable this serial console. And that makes me wonder, is there a library that USB in JavaScript? I mean, there is a USB API, but maybe somebody implemented the USB protocol in JavaScript. Yeah, I think this device is just this library just wraps the operating system. Let's take a look what it does. But I think it probably just wraps the operating system method. So yeah, there is like it seems like they just wrap libusb, so it's just a wrapper. It's not going to implement any kind of logic. And hi Tomasz, good to see you as well. Yeah, it doesn't seem to implement any interesting logic for us. Maybe USB protocol implementation. And I'm not very optimistic that we will find something. Or maybe, yeah, oh, it's on top of libusb. Not sure it's useful. Because I don't see why would anyone need this other than writing a simulator. But yeah, it seems like they have some things here, so that may be useful as a reference because we need a USB CDC. That's the serial. So and we also need like the host side of things, and here it might implement the peripheral. So yeah, I'm not sure. But yeah, this utility to parse USB descriptor might come useful. Yeah, and yeah, it doesn't really look very sophisticated, so worst case we can implement it ourselves. All right, let's go back to the docs. So there is like this diagram, which is an analyzer trace of the low-level USB. So we can see here there is like this reset, which probably is the host resetting the bus. And then there is transfer. F is probably flags. Get address 0, endpoint 0. It's probably a control. That's probably, there are like a few types of transactions in USB. There is like control, bulk, isochronous, and another one, I think interrupt. And then this is like the address and the endpoint, and I'm not sure if this is the address of probably of the device. And then the endpoint is like you can have multiple endpoints, which are like I think they are like ports on TCP, if I'm not wrong. So you can read and write from multiple places, and each one can have a different function. And then we send the device a get descriptor request, and that's the type of the descriptor we are trying to read, I guess. And then that's the device type, and then the device probably returns the device descriptor. I wish they had some legend for the colors, but they don't. Anyway, we can see like then the host asks to the device to change the address to address number 7, and then since that point it talks to address number 7, and then it reads the device descriptor again. It reads the configuration descriptor, and then it reads few string descriptors, and then the device returns like this Pico test device. That's probably the device name and the manufacturer name. And finally, it tells the device to switch to configuration number 1, and then the device probably sends 12 bytes to the host, I guess, out. I'm not sure. But anyway, there is like data going 12 bytes going back and forth between the host and the device. Okay, and here we have like all the registers that are involved. They probably walk through the example. All right, yeah, that's a lot of code. And finally, as usual, we have the list of registers. So yeah, the USB registers start at this address, and then actually there aren't too many registers, given that all those registers are like the same, and they are valid for host mode, which we are not interested in right now. So we have this address endpoint, main control. Yeah, and like a few interrupt registers, and yeah, those are device only. Yeah, there is a bunch of registers, but not too many. Less than I feared there would be more. All right. And then there is like this SRAM, which is used for the data, and I don't think they I found out where it's. Hey Graham, good to see you here again, or maybe not again, and I don't remember actually if you were ever joining us for a live stream. Anyways, yeah, there is like yeah, so the DPRAM is mapped here, and then there is like the USB registers, then 10,000 hexabytes later. Let's see if there is anything interesting about this dual port RAM. Yeah, USB. Oh, that's nice. So if you are not using the USB, you can actually use this memory as like for whatever. It's free extra memory. Yeah, so I think the first thing we should probably do is create some structure or buffer to hold these 4 KB of DPRAM. So let's go. Oh, so first time live. Cool. So yeah, So welcome to the first time live. So let's see. Let's go back to the main class and add read-only USB DPRAM new uint 8 array, and that's 4 kilobytes. Yeah, I think we can probably make it a bit more friendly by just adding. Then we can, instead of go away, instead of writing those things, just write it this way. Probably easier to read. All right, so we have this USB DPRAM, and let's map it so it will be readable and writable. Uint sec32. Yeah, let's add export const DPRAM start address equals to this, and let's also add the end address, which is just 4K later, and then we can read uint 32. So if we have let's see, so yeah, we can actually remove the end address because we can do the same trick, this dot usb dpram.links. So usb dp or dpram start address. Yeah. All right, so if it's within the DPRAM range, then this dot usb dpram. Yeah, we need to create a view for it, so we would be able to access it in different word sizes, so either 1 to 8, 16, or 32 bits, and it should read from the DPRAM buffer. And we said we don't need this DPRAM end address because we just use the size, so uint 32 read. Okay, so we wired this DPRAM, and let's also wire it to writing. So write uint 32, and then if this address is the DPRAM, then just set uint 32 address value and true. Okay, so DPRAM wired, and now once we are done with that, let's start working on the registers. So the registers, I guess we could just use another peripheral like we did with the rest, even though it's not a standard peripheral. But how did we do the PIO? Did we configure it through the... No, we actually had a spatial if case for the PIO. So maybe we should have one for the USB. After all, it doesn't behave, it doesn't have those atomic rights, as far as I can tell, and all of that behavior. So let's add another, yet another if statement. So if it's USB register space, then just, read from the USB CTRL, and we'll define the USB CTRL in a moment. Oh, we do have this USB CTRL already. So, but oh, we want the reg base. Right. Uint. Right. Read uint 32. And then same goes for write. writing uint32. And then write uint32 address and value. So all we now need is this magical USB CTRL, and we have USB simulation. Let's create it. Read only USB CTRL, new RP USB controller with this, and there is only one, so we don't need to. Maybe we'll give it a name just to stay consistent with the other peripherals, but it doesn't need any other parameters because there is only one. So it can be whatever we have, like the interrupt number and so on, can be hard coded. All right, so let's create in the peripherals another one, usb.ts, export class RP USB controller, and it extends space peripheral. So let's import it. And yeah, I guess at this point we should probably just implement the skeleton for reading and writing uints, and then we'll figure out what to do with them. All right, so yeah, we don't need this, just the structure for now. Yeah, empty switch statement, that will be fixed in a moment. And yeah, I guess what we can do in order to figure out the important part for us for now is just starting by running one of the examples. I guess the one that is interesting for us with USB CDC, there is like this hello USB. Let's try to run it and see how it interacts with the USB controller. So let's just take a look at the source code first. And if we were to implement the whole USB thing, then I would probably start looking at this device low-level example, this one, which is also mentioned in the documentation. As you can see, it takes quite a lot of code just to implement a USB device from scratch, even though it's nicely documented, so the actual code is a bit shorter, I guess. But in our case, yeah, the host just uses a tiny USB example, I guess. But in our case, we just want to get the serial, the CDC to work. So let's take a look in the hello USB. So yeah, it just initializes stdio, and I guess in the CMake configuration file, we tell it somewhere that we want to enable, yeah, to enable stdio USB and disable the UART. So that's probably the difference between compare. Do we have yeah, or there are other differences because probably the name of the example changes, but yeah, you can see there is this is like the biggest difference between hello USB UART and hello world UART and hello world serial. What is that? Not building. Oh, if you don't have tiny in the SDK. Okay, if you don't have tiny USB, then you get this warning. But we do have, so we should have these files here, these build files. Yeah, let's copy them to our working folder. So build USB. That was the build hello world USB cplo usb.uf.hex. We don't have a hex here. Oh, we do. And hello usb.elf to our working folder js. Okay, so now we should see them here, and we can try to execute it and see what happens. I mean, nothing interesting will happen because we still don't have USB, but Let's see what kind of reads and writes we get from running those. So there is like this demo and then emulator run, and then instead of running a low UART, let's run a low USB and npm start, and let's see what happens or what not happens. Ooh, a lot of output about wait for event and set event. I think there is a way to disable this, but let's just go to the instruction file, instructions, or is it? Oh, it's right in the ARP2040 WFE. Yeah. So we have the logger here, and do we do anything with the logger? Not really. Logging. So there is this const logger. So for now we can probably, what's the level of this missing instruction? RP2040, it's log info. I guess we can just disable those info logs for now. So when we have the logger, we can decide the log level that we want. Maybe here we have like code, yeah. So let's only log above warning, so we don't see all those things. And let's see, yeah, we get a bunch of writes to undefined addresses. I think that's the flash configuration, so it's not really interesting. What is this unimplemented? Yeah, QSPI base, but I see nothing from the USB. Yeah, let's see why. Maybe we just don't log this, or base peripheral. Right, uint. Yeah, it should write a warning if you have unimplemented read or write. Let's just be sure. Console.log USB read USB write, just to make sure we aren't missing anything. And if not, we'll open GDB and see where we can get. So yeah, I don't see any missing read or missing write. So let's start by opening GDB and seeing maybe it's like waiting for some pin or something before it initializes the USB. So let's create another terminal, and I think I need to configure my IP whenever I restart the machine. So let's do this. Yeah, so let's add it to the hosts, win host without ES, a single one, and now we can run GDB multi-arch. Let's load this file that was low usb.hex and target winhost 333 and see where we are at. Target remote winhost. Yeah, it didn't find. Oh, we want to load the elf file, not the X, and this is probably a low underscore USB. Yeah, sleep until frame 2. Yeah, I guess I haven't built the SDK with debugging symbols, so we don't get too much info. I mean, with symbols, but not with the complete debugging info. So let's rebuild this example with all the debugging info. mkdir build, cd build, and then there is like this flag to CMake that I always forget, but we can find in the getting started guide. Yeah, that's build type equals debug. And it's, oh, I need to set it Pico SDK path, and now it will work, and I will be able to properly debug the example. make J32, so it happens really fast. And then I will just copy again those files again, and we'll hopefully get all the debugging symbols that or information that we need. Let's wait one more second or a few more seconds for it to finish, and cd hello USB, and then we had those two copy commands. Yeah, one copy command, even better. Now we can switch to the other one and restart this simulation, and also run this GDB. Yeah, so what's going on right now? Where are we? Frame. Oh, now we can see the stack trace. Yeah, I think it seems like USB. It seems like it does get into main and prints the hello world, but it doesn't seem to. We don't see any indication that it writes to the USB controller, which is a bit weird. We have set this up. Yeah, let's try to take a look at the listing to see if there are any interesting methods where we can put a breakpoint. So that would be the build for the hello world USB, and we have this listing file, and maybe inside stdio USB out characters. Yeah, let's try to put a breakpoint here and see if it helps. So first thing, let's change this script not to automatically run the code, so we can set the breakpoints before the code starts running. And let's break here. Actually, we can just restart GDB, that would be faster. Break here and continue. Okay, so yeah, we can see here we are inside stdio put string, and it called this method. Actually, I'm thinking it might be easier to debug this right from Visual Studio Code like we did last time. So yeah, let's remote open OCD. I think that's probably yeah, actually there is a nice example here in the examples which already configures Visual Studio Code, but don't we have our own configuration? Yeah, I guess I trust them. You don't have. I don't want to debug JSON though. I just want to. Yeah, there isn't probably a configuration. All right, yeah, now let's try to. I remember we did this, but maybe we did it on the SDK folder. Anyway, so that's on WinHost, and there is like this, where do we tell it? Yeah, the executable. Maybe we can just point it at a USB and that will work. Let's try that. I guess we could probably configure our IDE to automatically detect it with CMake configuration, but I wouldn't want, yeah, and to main, I wouldn't want to spend too much time on that. Let's try to run it and see. Open. Oh, there is a Cortex debug configuration. Okay, let's try to install this extension. It may be useful in a way, or I don't know. Let's try that. Okay, let's. Oh, it's still installing. All right, let's try that again. It doesn't know about this CMake path, so for now, let's just give it the path to the L file manually, and now it isn't happy about GDP target does not support this command. Yeah, we didn't implement monitor remote halt, I guess. Yeah, there used to be another type of configuration that worked for us. Maybe it's in the we have this file in the Pico SDK. Let's see. I remember we had this in the past. No. Yeah, I don't remember where, but maybe if we just create a new debug configuration, or if I just undo a bit, I will get to the default. So cppdbg sounds good. cppdbg. Yeah, it's still executable launch. Yeah, all right. Okay, let's go back to GDP for now. I think that should be where are we anyway? Okay, interesting. No. Yeah. Hello USB. So we wanted to breakpoint at this function. Actually, let's take a look at what it does first. Pico SDK. No, not Pico demo. Come on, leave me alone. Pico SDK. Yeah. Right. So let's find this function and see. If TUD-CDC connected, then it writes those characters to probably, I don't know what's TUD, maybe tiny USB stuff. Yeah, it's inside live tiny USB. So I guess tiny USB device CDC, right? So that's calling it tiny USB stuff. So let's see what happens there. stdio. Let's set a breakpoint here. Continue. Oh, this died. Break here. Continue. Let's maximize this layout src, and let's see what's going on. It gets the, where are we right now? Okay, I guess, yeah, I guess tiny USB hasn't initialized, so tiny USB CDC connected returns 0. This returns TUD, and this reads from here. Whew. A function that calls another function that calls another function, but where is the implementation? Is this a global thing? This, yeah, okay, cool. So we can probably find a bunch of information just by printing this structure, so we can see it's not connected. Basically everything is 0, like as if it has never been initialized or something like that. And then I guess there is like some kind of initialization that we can probably hook to. Hey Nekati and Francisco, the party is getting bigger every moment. That's nice. Welcome. So yeah, let's see if there is like anything that initializes, probably in stdio init, USB init sounds good. So yeah, let's see what this does. stdio USB init, TUSB init, and then I guess there is like USB IRQ, so maybe it's waiting for interrupt from the USB. And what does TUSB init? Let's set a breakpoint there and see what it does. So let's restart this. And break, that was TUSB init, right? TUSB init, yeah. Okay, so it should init the device stack. Okay, and then it's not initialized, so we should get here, and then it creates a mutex, and oh, we got out of init. Okay, interesting. And then it sets up this. Yeah, I guess it's not interesting at this point. At this point, USB should have already been initialized, but we don't see any writes to the USB. So I guess we probably missed something in TUSB init. Which called, I think, TUSB init device, if I'm not mistaken. Let's try that again. All right, so break TUSB init. Next step. So it called to the init. And this probably just clears some, yeah, probably calls memset. So I guess we can run to return, and then it created this mutex, and then it creates this device queue, which probably is just some structure in the memory, not very interesting. And is there an app driver? Yes, there is an application driver. Let's see what this driver does. USB-D driver count equals 1 returns. Okay. And then there is like a bunch of drivers. Yeah, there is like this driver, and it has init, reset, open, and let's see who implements this driver. So there is like reset d init. Okay. That's inside the Pico STD IO USB reset interface. Okay. And with the second driver. CDCD init. That sounds like something that might be interesting. So initialized TU FIFO config. Okay, CDCD init, and then it initializes the class drivers. I think the device controller driver sounds like something that could be relevant. That's, yeah, DCD RP2040. Yeah, I think this is where we should probably see some writes to yeah, so it writes to the resets block, probably to reset the USB. Then it clears some stuff, and then this seems like it's going to start writing to the USB 8 hardware, right? But for some reason we don't have this symbol. But I guess at this point, let's switch to assembly. So we are storing to 4 plus 116. Yeah, that seems like it's writing to the USB, and yet we don't see those writes. So we probably have some bug in the code, since we should have seen this write. But anyway, that's like, let's open the source code for this. P24 USB init. Oh, Graham says in the chat that Hello USB does not wait for USB connection before printing to the void. So if we don't have a USB connection, which is the case right now, it will just print to the void. So yeah, I guess this is where we looked at, and now we need to figure out why we don't see those writes. Cool. So yeah, we can probably close GDB for now and start figuring out what we messed up in the code, now that we know it's our fault. RP2040 and write unit 32. So we added this case where if this is USB regs control base, then we are calling this, and this should print USB write. And this seems about right. Yeah, I don't see any reason why it wouldn't work. I guess we don't have any peripheral in this address, right? I mean, we only have peripherals. Where do we initialize them? Yeah, probably here. Yeah, we don't have anything that starts with 50 hexa, so that's very interesting. Yeah, what we can probably do, we can probably try to debug this, I guess, and then so let's set up to run this in the debugger. And then we can connect to it from GDB and, you know, see what happens when that. So we want to create a Node.js debugging setup, and then, yeah, it runs the index file. That's not what we want. Where is the launch JSON? VS Code. It doesn't create any launch. There is like debug. There is like a way to create this launch JSON for us, right? We don't have to Google this. Or maybe we do. Yeah. Create one for Node.js. Okay, fine. And then we have like this PWA node. No, it's just node. Or I don't know why it's PWA. Anyway, it should run. Can it run? Let's see. TS node debug VS Code. Yeah. At the end, we always turn out to Google. So yeah, it just compiles it in order to debug it. Launch program, and then this is like the program is actually a demo that was emulator run.ts. Oh, yeah. And then there is like this pre-build task, pre-launch task. Yeah, it looks good, I guess. Let's try to see if it works. Maybe we should also configure this task. Let's try to see what happens when we run it. It did run TSC, but we probably need to provide a configuration that will also compile this demo. Isn't there a way to just debug it without without compiling it first? Yeah, that sounds probably better. Yeah, let's try that. Launch JSON. And it should run this. And we don't need any other arguments. Yeah. Okay. Maybe now it will work. Yeah. Yeah, you can see it had some issues, I guess, but now it's listening on port 333. Let's try to set a breakpoint in write uint 32 and see if it actually stops there. Yeah, but for some reason I can't set a breakpoint. Add breakpoint. That's strange. Let's try to stop it. Oh, for some reason, I guess the test utility interferes with my ability to add breakpoints. Let's stop it. So yeah, now I can add breakpoint freely. And let's add a breakpoint here and see if it stops here when we start the code. GDB multi-arc, yeah. Let's just break inside, that was DCD init. Yeah, we can see it stops here, which is great, but we do want to run this for now. Layout src, next, next, next. Yeah. All right, and now let's switch to assembly, and this is probably this str is instruction. Let's print R3. Yeah, this is going to write, so we should stop here in the simulator write uint 32. Yeah, and now let's see what happens. So we have this address, which is probably a good one, I guess. Let's just hexate to see if it's... Oh, wait a second. It doesn't seem like the address we wanted to write to. Interesting. What's the stack trace? Process GDB message. Oh, it's probably GDB setting some breakpoint. So let's keep going. And then we have another address, which is probably again GDB. Yeah, I mean, we can see from the stack trace that the previous one didn't come from execute instruction. Only this one actually comes from execute instruction. So now we are writing to this address. Let's see if this address makes sense. No, I want the terminal. Where did it go? Yeah, so yeah, this sounds like the correct address, and let's see what happens. So we are reading, and yeah, it's not SAO. Oh, so that's the reason we ignore USB writes. Yeah, and if we had like those this logel still enabled, we would probably have seen this message. So I think we found the culprit. Let's see if we also ignore USB reads. yeah, so cool. I think the debugging session was useful. And now we should probably, if we just run it again, we should probably see those USB writes. But before we try that, let's just make sure we don't have like anything that ignores. Yeah, we can see that now this variable, this constant became unused. So probably let's just double check that we don't have any code that ignores the USB reads for us. No, it doesn't seem so. All right, so let's start that again, and now we hope to see a bunch of writes to the USB peripheral. Emulator run. All right, let's see. Yeah, a lot of USB writes. Cool. So yeah, now we can see how the code starts to interact with the USB peripheral. It just resets a bunch of all the registers, I guess, or most of them to 0, and then it starts writing stuff there. So first of all, let's remove those extra console logs. We don't need them at the moment, and it's only writing, it's not even reading anything, which is interesting. And let's try to decipher those offsets. I mean, we are writing to 74, 78, 40, 4C, and 90. And yeah, I don't know, this is like hexadecimal. It looks too big to be hexadecimal, so I guess it's just yeah, just a raw value. Okay, wonder what is this value. What does it look like in hexadecimal? If it has any meaning. Yeah, it's the start of the RAM, but it's probably some flag that it's setting. Okay, what is this write to undefined address? Where does it come from? I think this is still in the USB registers region. I think it's probably a bit bigger than what we defined. Right, UN32. Let's see. Yeah, ooh, USB CTRL reg. Yeah, we thought it's 1000 hexa, but it's probably a bit bigger. Even though it seems like from this description, it doesn't seem like there are any registers like after 1000 hexa. So I wonder how comes we get this right. Yeah, I guess one thing we can probably do is just set a breakpoint here and then see who writes there. So let's do that. Oh no, I want to run it in debug. Let's just change the configuration to, we don't want this breakpoint anymore. And yeah, is this the address that we wanted to? No, that's not an interesting undefined address. Yeah, there is a bunch of those which we don't really implement. Many of those, I guess, as we can probably see here. Yeah, there is a bunch of those from the QSPI base. Oh no, that's, yeah, that's a bunch of those writes. And I think we went too far, probably. No? Okay. And yeah, let's take a look at the value we are looking for. Oh, it doesn't say which value we had. this address, but let's take a look at the decimal value. So it should start with 13 when we get there. Oh, we found it. So let's see where we are at right now. Yeah, we should probably have like this here somewhere, this, and then we can take a look at the PC. What is the address of PC right now? And yeah, and then we can take a look at the listing to see who is writing there. What's the code that writes there? Yeah, that was in the Pico examples. Yeah, this store in DCD Connect. So let's take a look at DCD Connect. USB HW set. Interesting. So it seems like USB does have atomic writes enabled, I guess. Does it say anything about that in the datasheet? That's for the atomic register access. So each peripheral 4K. Yeah, I guess it does support those atomic memory access. So in this case, it might make more sense just, you know, to add it to the peripherals array instead of having a different switch case for it. Yeah, so let's do this. So where's these peripherals? First of all, let's find the address. Now the DPRAM, USB CTRL. Yeah, now let's go to the peripherals and just add this one. New RP USB controller, this USB. Or we can probably just do this.usb-ctrl. I don't know if we will. We'll probably need to expose it to the user, so the user can hook like we did with the UART, so the user can hook to the output. Okay, and then we can definitely remove those ifs from. We don't need those. They are covered by the peripheral access. And write uint32 as well. All right. Yeah, and then we probably don't need this USB CTRL. Yeah, this register anymore. And now let's try to run this again, and we should not see this write to undefined address. Yeah. We can just see there is a bunch of reads and writes unimplemented. So yeah, we see those registers. Let's see what they mean. 74, 78, 40, 4C, 20, 90, 4C. So list of registers. 40 is main control. And 4C is SAE control, and 90 is interrupt enable. So we have seen that it enables the interrupt, and then again 4C is SAE control. So I guess these are like the interesting registers. What does this do? Okay, so it doesn't have a lot of bits. Reduced timing for simulation. Interesting. Maybe this can be useful for us in some way. Not sure what is that, but It does seem interesting. Is there any other mention of this? No. But it just enables or disables the controller and selects between device mode and host mode. So I just, add a constant for it. Const is 40. And then there is like this other register, SAE control. What is SAE? I have no idea, but it does seem to have a lot of bits. So let's take a look at the code that initializes this maybe. So yeah, we can see it enables or disables the pull-up resistors. I wonder why it called DCD disconnect though. I wouldn't expect it to call it when the program starts, so probably something failed in the initialization. Let's take a look at that. Let's restart this. Yep. And where is this emulator run? So it doesn't automatically run. And let's see which flow led us to this DCD disconnect. Break DCD disconnect. Or maybe not. Yeah, something. Oh, that's GDB reading stuff from the memory. Not really interesting. Yeah, I'm pretty sure we had this thing. Oh, maybe it was DCD connect, and yeah, probably I looked at the wrong function. So never mind, it never called DCD disconnect. I guess we are all good. Then, yeah, let's go back to deciphering what it does to set up the USB. So DCD init, and DCD is like for the serial, I guess. RP2040 USB init, and then it initializes to one endpoint 0, and yeah, we can see it says it enables those interrupts. So there is like a bus reset, there is a setup request. So I guess one thing we should probably do, as soon as the peripheral enables USB, we should probably send a bus reset to tell the device that, hey, we are here. So let's try to see who listens for this bus reset. I'm not sure how it works on the actual device, but yeah, this is the IRQ handler, and we can see there is like bus reset. So yeah, maybe we should try to go the other way around and see what happens when like when it writes. We had this function which was writing to, yeah, this one, CDC connected. So let's see where we set this. STDIO USB. HUD ready. Yeah, not HED, CDC device. HUD mount HUD. Yeah, so it's mounted if it has a configuration num. So I guess, yeah, there is like this USBD dev. Maybe I will start taking notes before I forget. Structure with all the information about USB device. Okay, and then there is this CFG num. So if it has a CFG num, then it's mounted. So let's see who sets the CFG num. Yeah, so we should get send the device a set configuration request in order to and probably before that we should send it a set address request. Yeah, so that should probably be a control request. And who calls that process control request? TUD task. So the TUD task, tiny USB task, gets event. Where does it get the event from a queue, USBD queue. So who queues those events? The events are queued by DCD event handler and queue create. Yeah, it's probably from this DCD event handler. I think that's the only place where we send where we send stuff on this queue. So let's see who calls this. So DCD event bus signal, bus reset, setup received, transfer complete. Yeah, I guess somebody calls those methods. Let's see, bus reset, who calls that? That's probably per port because there are like many implementations. So let's take a look at the RP2040. Yeah, there was this file with the RP2040. Tiny USB portable Raspberry Pi. Yeah. So this is like where we are sending the events, I guess, in the IRQ. So we probably need to enable this to implement this IRQ and start sending this IRQ as soon as there is a device on the bus. So let's start by taking a look at so we have like this, there was this USB. So when we write to main control equals 0, it can be private. So when we read from it, we'll just return this dot main control case main control, and when we write to main control case main control, we are going to do reset the device, and then this dot main control, or only if the USB is enabled in device mode. So let's set up the bits for this. That was inside main control. Main control bits. Timing is 31, and there is also host and device, which is just 1, and controller enable, which is 0. So if value and probably just all those we only want the other bits are reserved, so we are not interested in them, only those bits. And then if value and controller en, and we also want to make sure that we are only device mode, value and host and device. Then we want to reset the device, and for that we would need to enable this interrupt, or to trigger an interrupt. And let's see what is the interrupt number for the USB controller. So it's here, interrupts, and USB is number 5. And then I guess we have like the same pattern as with the other peripherals, where we have like some register that includes the flags for the individual interrupts, and then a bunch of enable registers, and we can probably just copy the same logic from some other peripheral. Let's take a look in list of registers. So we have this row interrupts, interrupt enable, interrupt force, and interrupt status, and we have 20 different interrupts. All right, so let's start by and so the interrupt status is read only. We can't I guess yeah, there are like a bunch of ways to clear those. Some of them can't actually be cleared. Yeah, we'll have to take care of this logic, but for now, private inter equals 0, case inter, return this dot inter, and the inter is at this offset, const inter. Okay, and then we have interrupt enable, which is int e. Int e here, this one, and then we have int force at 94, and ints, which is probably just the combined the final interrupt value after enable and forcing. And let's just copy this logic from another like peripheral. Maybe we have something similar in the timer. So yeah, it should probably have, yeah, let's call it, let's be consistent with the naming. Int row, int enable, int force. Maybe at some point I will just move this to the main peripheral because it pretty much repeats. But on the other hand, there is like a very little code that repeats. I guess only the variable definition and the int status, and then maybe a code that checks if the interrupts have been updated, because the offsets, they change between peripherals, so we couldn't just copy this code as is without configuring those offsets somehow. Right, and then writing, and yeah, and then check interrupts is probably also repeating. Yeah, we can't write to int r, only to int, because it's read only to int e and int f, and we have 20 interrupts, so we need to enable 20 bits, so that's 16, and 4 more, that would be 20. Yeah. So same for int force, we only need 20 bits. And let's also copy check interrupts. So if yeah, so basically, if we have any interrupt, then we need to set interrupt the USB interrupt. That's USB control IRQ. All right, so now when we have the interrupt logic, we can also reset the device, I guess, just by, let's take a look here. So bus reset, what is SAE status? Probably that other register that we have seen being written to. List of registers. No, that's the control. There is SAE status, which is write clear. So this probably clears most of the interrupts. And yeah, so we need to set this bit whenever we reset the device. So maybe we'll just create this private reset device, and then it will just let's SAE status at 50, and then in this case for reset device we are just going to this SAE status or equals SAE bus reset which is bit 19. Private SAE status, the default is 0, the reset value of all of those. And I see that some of the bits are read-only and some are write clear. So yeah, we have some work with this register. All right, so let's make it easy to read it. And let's implement SAE status bits. So there is this bus reset, which is bit 19. And then here we can just call this dot reset device. And yeah, I guess we should also this dot row intro. We should also set this flag that tells that we have this that we had this reset condition. So that was bus reset. SAE status dot bus reset. I mean, another way to go about it would just be to copy all those bits from SAE status into, yeah, there is like a bunch of like bits that are just copied. So instead of like duplicating it every time when we write to SAE status, let's this dot status updated and SAE status updated, and then we can just update those bits specifically. So yeah, there is like this, all those interrupts that come from SAE status. Yeah, I'm not sure. Some of those are probably also coming from SAE status, but let's start with those for now. Most of them are coming from the SAE status. Okay. Yeah, we don't need all those. All right, so then we have like bits 5 to 16 that need to be copied from SAE status. So this dot intro bits 5 to 16, so that would be 4, 5. Yeah, maybe I will just let's see where I guess they are not copied from, like, yeah, they are copied from different locations, each one. So we should probably, this is SAE status, right? We should probably sort of have this mapping. Let's just have copy this into, yeah. Actually, there might be an easier way. Instead of copying from the datasheet, there is like this hardware description file in the SDK, which is probably easier to copy from, maybe. Yeah, I guess we could structure that one faster. Let's try that. Then, like, pasting from the datasheet. And then, yeah, and then we only need, we can get rid of all the descriptions. So yeah, we don't need fields, and we don't need access, and yeah, the only question, yeah, this spans multiple lines. Yeah, maybe we should have written a tool at the beginning to just, you know, convert this into JavaScript code instead of doing all those copy pastes, but we already did them, so whatever. Yeah, we don't need this as well, and this one as well. And now we can probably, yeah. Now we can probably do some heavy editing to create a constant. And there we go. I don't know if that was faster than copying from the datasheet, but surely if we need to do it a few more times, then I will get better at this. And then, yeah, and then we need to, yeah, I guess I will just make it like that. Yeah, so this one comes from this, and I just want the sources for each one. And 14 come from this, and this one comes from here. This one comes from here. Yeah, we can do a few at once. And this one comes from here. And 2 more to go. And we finish with this register. Okay, and then we can probably have something like we have this map, const int register map, and then we can have probably a list of, or just an object that maps each of those values into its corresponding bit in in the inter register. All right, and then we can say something like this. So let's move those values to the end, and instead of SAE status, it would be this equals this, not equals colon this. Almost happy. Just one more thing, it's not happy. There is no VBus detect detected. Okay, so that's probably a copy paste problem, right? Or maybe not. VBus detect comes from USB power. Yeah, that's probably a typo. It should have been VBus detected here and not VBus detect. Okay, where do I send pull request to file issues about typos in the datasheet? Graham, can you point me that way? Okay, so now we can for const SAE bit of object.keys int register map. Actually, we can take both the key and the value, so SAE bit and int r bit, int row bit, this.int row. Let's clear this. We can probably have them shifted already here for us, so we don't have to to be consistent with how we do things here. Just pre-shift the bits. So it's intro bit. So we are clearing the intro bit. Or we can do if this.SAE and SAE bit, then we will set the intro bit, otherwise we'll clear it, basically mapping between those two registers. All right, and it's not happy because an issue against Pico feedback. Okay, I will do it. Let me just write it down so I won't forget it. So we have this thing where VBus detect should be VBus detected. Not a big deal, but maybe, I don't know, maybe it's important, maybe not. I'll submit an issue and we'll see. And it's not happy because this returns an iterator. Oh, I don't want values, I want entries, key and value. And then, yeah, a key of an array is always a string. So maybe let's just make them instead of, I don't see a reason to make it an object. We just, we can make it just, a list instead with 2 items per entry of int register map. Yeah, now TypeScript is happy. Yeah, and we have a few bits that do not appear yet in this mapping, but at least at this point we can probably safely reset the device, and let's see if this works. So if this works, we expect to get to, let's see, that was inside the SDK. Yeah, that was us, the SDK. We expect to get to this event handler. Basically, eventually we expect to get here to DCD event bus reset. Let's see if this happens. Let's restart a simulator. But first of all, let's set up a breakpoint in GDB. And then now we can attach and break here, continue. And unfortunately, it didn't happen, even though we have probably sent this interrupt. Let's double check if we do what we think we do. Let's add a console log there. Console log resetting device. Oh, I know what the problem is, or no, I don't know what the problem is, but we can see it gets into this device reset, and the interrupts should be enabled. I think, yeah, 74 and 78. What are those? I think one of them, those right, was for the interrupt, so maybe that's the problem. 74, no, USB power and muxing. Yeah, not seem very, yeah. 90 was enabled, and I think we don't see that on the list of, yeah, unimplemented writing. What is 98? In status. Is it writing to in status? I think it's read only, right? That's interesting. So why do we get, I guess there is a code that just, you know, initializes everything to 0. Otherwise, there is no reason to write 0 to in status. Okay. So, yeah. So there is this write to 78, and we return to main controller, reset the device. I guess after resetting it, we should call check interrupts, because we have, maybe here, because we may have updated this intro. So I don't think this is the reason we haven't seen. Let's console.log and check interrupts, whether we get console.log check interrupts and in status. And let's see what's going. npm start. Let's see if we do get into check interrupts. Yeah, we do get, and we probably do raise this interrupt 496. So let's take a look at the interrupt handler and see if we get there. This is probably this one, right? Yeah, it looks like this. This is the right one. Emulator, MCU execute. Okay. Rake here. GDB is tired. It's very tired. Let's, oh, it probably, I'm not running. So it's not tired, it's just having trouble connecting, and it won't complain. Yeah, all right. So interesting. We don't get into the IRQ handler, even though I think we definitely have code that raises this interrupt. Is this the correct IRQ number? It's probably defined here. Yeah, that's 5. Interesting. So what could the problem be? Why don't we get into the interrupt handler? Yeah, so we call set interrupt IRQ, and the value is true. Let's just, you know, to be sure. And then it will have pending interrupts, and it should probably raise an interrupt. Raise interrupts updated. Exception entry. Yeah, and then we can probably if interrupt number equals 5 console log USB interrupt. Let's see if we get here, or did we miss something? And yeah, we also want to automatically start a code without waiting for GDB. Yeah, interesting. It doesn't get there. So let's try to figure out why. Interrupt number. Set interrupt. So if IRQ equals 5, console.log, maybe after this pending interrupts, this dot pending interrupts. Let's see what happens now. Do we get 20? 20 is, yeah, it sounds like bit number 5, so it seems to be pending. But why don't we get into the IRQ handler and check for interrupts? That's strange. What is level interrupts? Interrupt set, interrupt priorities. Yeah, maybe we should try to debug this. So let's set a breakpoint here and run this in the debugger, and then see what's going on inside. Check for interrupts. So yeah, we are here, and then let's set a breakpoint here and see what's going on. Yeah, check interrupts, pending interrupts 0. That's still not the interesting place, because we still don't have, yeah, now we have a value. So now we can set this second breakpoint and see what happens. So now we should have a pending interrupt, right? Yeah. This dot level interrupt is 0. Probably somebody has disabled interrupt priorities. Priority 0. Oh, right. Maybe for the next level. Yeah, it's always 0. The current priority is 2. So yeah, interesting. I wonder where this -1 comes from. This might be an issue. So at the beginning, all the interrupts are in priority 0, I guess. And then when we write to the NVIC, yeah, there might be some bug here, because I think all the interrupts, I mean, yeah, it means all the interrupts are at level 2 if it's -1, because it's all Fs. So why is are we inside an exception handler right now or something like that? I mean, we would expect, let's stop here. So we would expect the current priority to go above 2. Where do we get the current priority from? This.IPSR is not 0, and does. All right. So current priority is now 4. So at this point, we do expect it to take the interrupt. So priority 0, priority 1. Now with priority 2, we should see that there aren't any interrupts. Why is that? Pending interrupt set to 0, even though I don't think anybody cleared this interrupt. That's interesting. How did it get to be 0? That's one place where we clear interrupts, and also writing to ICPR clear interrupts, and I think these are the only places, and also calling set interrupts. Okay. So yeah, something clears this interrupt bit before it's fired to the program. Not sure what that would be. Did we change anything? Yeah. Let's restart this debugging session and try seeing where this is getting cleared. So yeah, we don't need this breakpoint for now. Let's run until, yeah, now the interrupt should fire. And now let's just add a breakpoint whenever we clear pending interrupts to see why it's cleared. And let's run this, and we can see this one clears the interrupt. And where are we where this happens? This is undefined. Interesting, but we do expect this to be the instance. Maybe if we execute step over, we'll have this set. No? Okay. So where are we right now? In right uint32, and now we can see this and see which memory address cleared this. Actually, at this point we can probably attach GDB and then see exactly where we are. But let's first of all, just to make sure, copy the value of PC. And yeah, now if we run it and disable those breakpoints, we can probably see where we were, or maybe not so. Okay, but we did copy the value of PC. So let's see, where did we disable this interrupt? Or clear this interrupt flag. IRQ set mask enabled. All right. So yeah, let's try to, I guess, set a breakpoint there and see how we get to this place where we disable the interrupt. So we'll do this. We need a breakpoint at this address, and also first of all we need to break in this USB init. So when it enables the setups the USB controller, that was inside here. So I guess at this point, yeah, we can probably find this specific point in the listing file, or just break here and run line by line. Let's actually try to find the specific point that was in the Pico examples. inside DCD init. So yeah, I think that was writing to control was 40. So this is probably the place where we are writing one to enable the USB controller. So let's start with breaking here, and then we'll set up another breakpoint and see who is that person who is clearing the interrupt flag for us. And yeah, so let's run this again, execute, emulator run, and comment this and start. All right. Oh, actually I wanted to comment this out, so it won't run the code until we attach GDB, and then we can execute those commands, break, continue, and now you can see we are initializing, so we can set a second breakpoint, and at this point we'll probably have, after this peripheral write, if we continue, yeah, we can see IRQ set mask enabled. Who calls this? In DCD int enable in TOD init. Yeah, TOD init. So yeah, this is disabling the interrupt ISCR. In the RB2040 interrupt set enable. So why did we get into interesting, how comes, yeah, how comes this one actually cleared the clears the interrupts? IRQ set mask enabled. Oh, it depends whether we get ICPR, ICPR, clear pending before enabled. If the IRQ is actually asserted, it will immediately repend. Interesting. So I'm not getting something. If I'm understanding correct from this comment, it means that clearing this interrupt. So here, when we clear the interrupt, yeah, okay, Graham gives us a spoiler that the bus reset is happening too soon. That's interesting, because I can already see, like, I'm not sure. Can you elaborate on why it is too soon, or where should we have the bus reset happen? I mean, if we take a look at the code, then that was here. We have this handler, and then we have this bus reset here, and yeah, it should have happened probably after we enable the interrupt here. Like after this line, we should have the interrupt fire, or I don't think it fires here, because we have seen, like, if we take a look at the stack trace, do I still have that open? I probably do. Yeah, we can see that it gets all the way. I don't know if something is disabling interrupts or something like that, or I don't know why, but we got all the way here without the handler being called. So obviously, at least until TCD int enabled, where is that? That's inside tar init. Yeah, so yeah, maybe, so at least until we get past DCD int enable, I don't think the interrupt will fire. Yeah, actually, I'm not sure that that would be a problem, because the only question is like, and we can probably like once it works, we can probably check it out with a debugger. I mean, we can probably also delay, but I think maybe if this isn't set to true, then we'll have some problems. But the interrupt isn't enabled only until this this point, so it might be okay. But I think we do have a bug here, from what I understand. If we take a look at, where was that, in the Pico SDK, if we take a look at the comment here, yeah, it seems that was in the again, DCD IRQ set mask enabled. So if I understand, then yeah, exactly. Yeah, when we clear ICPR in our implementation right now, we just remove the indication that there is an interrupt from this peripheral, and I'm wondering, I think, and Ram seems to agree with me on the chat, that this is not the correct behavior. We shouldn't do this. So I guess there is no reason to clear, like at least for hardware interrupts, we should never clear this. When I don't really see any reason to remove the flag when ICPR is written to. Because the interrupt should be reasserted as long as the hardware says there should be an interrupt. So maybe we should change the logic to be similar to what we have in, I think it's set interrupt, it's here in check for interrupt. So only if it's more than the hardware IRQ, then we, what is the issue 22? Issue 22. Yeah, only the lower keep. Interesting. Seems that a Pico SDK code expect the NVIC to clear the pending interrupt flag. Yeah, that's probably for the software. Yeah, but Graham suggests to call check for interrupts again, but then we need to do it for each of the peripherals. And I don't know, I don't see any reason not to just copy the logic from here. I mean, I guess there is no reason for us to just, you know, we can probably remove this to do. I guess there is no reason for us to clear this and then just check it again with all the peripherals. I hope I'm not missing anything here. Yeah, we should probably at some point move this NV code into a different file instead of having all those read hooks. Yeah, so where was clearing the interrupts? ICPR. Okay. Okay, Graham, I will ignore it, but thanks for making those comments. So maybe we should just, you know, yeah, when we are writing a value here, we should probably, yeah, we can't really copy the logic because we need to const hardware interrupt mask. Yeah, we have in that place we are dealing with a single bit, and here we have like a bunch of bits that can be cleared at once. So yeah, and then we want to yeah, probably there is a better way to do it, but my brain is not very functional right now, so I think that should also do the trick, like just bitwise and this with the new value that we get to, or yeah, or no, we should just, yeah, that will do the trick. So just make sure that all those don't change by setting them to 1. So basically, if they are 1 and we bitwise and with them, then they won't change. Cool. So this should do the trick. Let's check if we finally get this reset condition. Yeah, I don't think we'll see anything different if we just run it, because we probably need to attach GDB and set a breakpoint in the handler. Let's try that. That was in, yeah, let's be optimistic and hope it will actually call this DCD bus reset, see if that happens. Yeah, but let's restart it. All right, break. Whoo, hooray! Yeah, we got to the DCD bus reset. So yeah, let's take a look what happens here. So it should probably deliver an event step, and then it will queue it, and then there was like this USBD queue that listens for the event. So there is like this task that we should probably breakpoint here to see if it, yeah, reset. It seems like this interrupt condition isn't cleared. Let's see why. Finish. And yeah, then, oh yeah, we still haven't implemented the write clear behavior for this register. So we get an interrupt, that's one step forward, but you know, before we move on, let's just commit this. Actually, this is a bit mixed up, so let me quickly copy it away, and then we can just commit this small change first of all, this small fix. So RB2040, just so we won't forget about it. That was in ICPR. So fix RB2040 and NVC, NVIC, ICPR shouldn't clear hardware interrupts. And I think there is even we have seen a reference to this in the SDK inside somewhere. That was inside RQ. Pi Pico SDK comment, or quoting this comment that says so yeah, so yeah, all right, so let's push this fix. And now I thought we had those interrupts figured out, but there are always surprises. Now let's just copy back all our changes. So there aren't many of them in this class, only the USB stuff, but still we don't want to lose all those. It will take us a few moments to add them, but why should we if we already had them? Especially this one. This was pretty annoying to find that we had this code to ignore these USB writes. Just wasted a bunch of time at the beginning. Okay, so we don't need this temporary fail anymore. And let's see, what else do we have? So we had this thing where we needed to implement those SAE bit clearing, and let's do it. So whenever we write to this SAE status, we should have there are a bunch of bits that may be cleared. Let's take a look at the documentation again. That was SAE status. SAE status. And yeah, so it seems like most of them are write clear. Let's see. What is SC? Oh, wait a second, this is another register, so we don't need to worry about that right now. So yeah, we can probably create a mask with all the write clear bits. And then there is this logic. I think we have it in the timer as well for write clear, because there is the thing where we need to check the row write value. Yeah, because yeah, so we need to check. We can say this dot SAE status and equals, and this SAE write clear mask, and we'll define it in a moment. And this should probably let us clear, and then of course this dot SAE status updated to make sure that yeah, we check for interrupts and we update the interrupts. So let's implement this one, const SAE write clear mask. So I would say it's everything except for connected, and so it's everything up to setup rect and also resume. So everything up to setup rect and also resume. Right, and we want just to OR them all. Gotta OR them all, and without connected, right? And everything up to setup rect and also resume. The rest are real only. All right, so I think we also have this behavior now in place. So at this point, I really hope we can finally get to the place where it's actually reset, and we can try to set up a breakpoint at USB DC 495. Let's see if that would work. Restart and GDB and break in that was USB-D.C 495. Continue. Hooray! Yeah, we got into this TUD task inside this worker, and it got into the USB-D reset. And what does the USB-D reset do? it does a lot of stuff, but probably resetting all the drivers, etc. And I think if I so yeah, that's nice. We see that things start to what are all of those? Those are like GDB stuff. We can probably remove all these check for interrupts and pending interrupts. We don't need them anymore. Console log check for interrupts, and I think we have, yeah, this other console log. Cool. So we got past reset, and we had a diagram somewhere which can probably be helpful. Maybe that was here. Yeah. So hooray, we got past this thing where we got a reset, and now we should read the device descriptor from the device, I guess. So for that, we should probably send another interrupt. But I guess at this point we should maybe we can skip this step and immediately ask the device to set the address instead of waiting for the descriptor, or maybe we can even jump one more step ahead and, you know, just call set configuration to set a configuration. If I'm not mistaken, we had this place where it looks at the CFG. That was maybe here. Yeah, no. It was here, TAD USB CDC connected. Yeah, I keep coming back to this one. And interesting. There is also like line state, which we should take care of. Yeah, TAD mounted. Yeah, we should also have like this configuration. So we should probably we can probably just write 1 to the configuration or something like that, and then get this to work. Now I'm doing an educated guess here. I have no idea. One thing we can probably do though is load this example into my real Pico, and then let's see what happens there. So we can probably just print the value of USB dev and see what CFG num it gets. So my guess that it would be 1, but I think it can be helpful to just quickly check it. So let's do that. So first of all, I want to restart it and load this UF2. This is my Raspberry Pi Pico bootloader, and then I'm going to or was this, yeah, let's also copy the UF2 here so we have it handy, and then yeah, I can open this directory and just copy this hello USB into the Pi Pico, and voila. Now let's connect to with GDB. And then we can probably print that was underscore USBD. What was its name? USBD dev. Yeah, so yeah, we can see this is like when it's initialized, so we can see it's connected, addressed, suspended. Let's actually copy this. So, and it has a bunch of whatever, all these endpoint status, but the configuration number is 1. So we need the configuration number to be 1, and we can probably achieve that if we set the configuration to 1. Yeah, let's take a note of this value. So that was P on physical Pi Pico. It's so useful that I can just run it against the physical device and see what's going on there. Okay, so connect address. So we need to find a way to set a configuration, and then maybe we can skip all the remaining steps. Maybe we didn't even have to do the reset. I don't know. But it feels to me like it was a good idea to do the reset. Now let's see who writes to this configuration, and then we can set a breakpoint there probably and see how to get there. So that was _cf. That was, yeah, we don't need this. We have this here. CFG_num. So who sets CFG_num? This is when we are unplugged, but we are not going to be unplugged for now. TUSB rec set configuration from process control request. So we should get into process control request, and who calls that? So we need to have a setup event, and if we have a setup event, then we call process control request. So let's take a note of this. Let's save it, so we'll have it for the next time. Just let's call it USB notes. All right, so set configuration. So we need this event first of all, and then in this event we have this process control request. It calls process control request. So who sends this event? This is the event setup received, and it gets this setup, and this is called from this Raspberry Pi with setup, and setup is just pointing to DPRAM setup packet. And this happens if we have this USB ints setup request bits. So yeah, so we need to, so to set configuration, we need to set this bit in. Let's just verify that we do have this bit setup rec. No. Where is that coming from? Where is that? List of registers. Intro. No, I'm not looking at the correct thing. No, this is the right one. Intro, and we have setup request. Okay, so it's just setup rec, and here it's setup rec. Oh, maybe there is where is this USB code? Yeah, I wonder why it's called setup rec here and setup rec with Q here. I mean, this makes more sense, but not sure, like at least it's sort of consistent. So, but in the SDK it's called setup rec with a key. Oh, wait a second. So here it's called setup rec, and here it's called setup rec, but one time it's with a Q and one time it's with a C, but I guess it's not a typo in the datasheet because it also appears in the SDK, so it's probably, for some obscure reason, it was intentional to spell request here, and maybe rec is received or something like that, and not request. Yeah, received. Okay, so it's not, even though it sounds very similar, setup rec and setup rec, it's once here it's for received and here it's for request probably. Okay, so we should set this bit to indicate that we have the setup packet, and then the setup packet should be in this memory address in the USB DPRAM setup packet. Let's ask GDB to figure out the address for that. So we still have that running, right? No, we disconnected. Oh, but there isn't a symbol like that. Yeah, I guess we can also like just break here, continue, monitor reset, init, continue. Yeah, and now let's try to print the address of this. Okay. Yeah, okay, so it seems like it's at the beginning, right? It seems like, let's stop. Yeah, it seems like setup is just at the beginning of the DPRAM. So, yeah, so in this SAE status, and it was just setup rec with C here, right? Yeah, so first of all, write USB setup packet to here. So I think the next thing we should probably do is figure out what this configuration packet looks like, and then we can write it and set those bits. So figure out what the packet looks like, and there are many ways we can go about it. I think we can take a quick look at what that's interesting. Graham says we should probably also set the address, which makes sense. If we look at the dump we have here, we can see there is this addressed. It doesn't store the address here, but there is this addressed variable that says that the device probably got an address. Let's see who writes there. Yeah. Interesting. So when setting the address has been completed, then we seem to set address to 1, but I don't see we are. Oh yeah, also when we yeah, but it's, oh, what's that? Only send up to EP0 packet size if not addressed. Yeah, I guess we should set the address, because I'm not sure if that would be a problem, because I don't think we are going to request any descriptors from the device, and that seems to be the only place where they check if the device has been addressed. But it does sound reasonable for me to set the address, especially when it's like the same, it's the next if state to setting the configuration. Yeah, cfgnum. Yeah, so I think we should also set the address. It's very simple, similar set. We just need to write a slightly different packet and then indicate DCD setup received. One thing we should probably figure out is when to send those packets. I mean, one way would be to know that the device has processed the packets, and I think that's the way to go when it clears the SAE bits, so when it handles them. So for instance, we can probably do something like that. If this.row write value and SAE reset, that was bus reset, right? Where we, yeah. So if this, then this dot, and we can probably implement those next time. So set device address, and let's set it to 1. Just for the sake of it, it doesn't really matter. Yeah, maybe after updating the interrupts and everything. Yeah, so private set device address, or maybe instead of setting, we don't know, whenever we when we finish resetting, we want to set a device address, right? So to do write USB setup packet here, and then we can probably do this one. So SAE rec setup received. But we still need to write a actual USB packet, and then here, if we have like if this dot, so if the code setup received, and there might be a better way to yeah, address, use the provided address. And there might be a better way to detect where we need, or we don't need, where is the first time that we can send those packets, but I don't know. I think this will work, so we'll try and see. Set device configuration 1. And I think down the road we should probably let the user of this class create some kind of API that would let them send all those like reset condition and device address and like request the descriptors, but that would require implementing sort of a mini USB stack of our own, which I don't want to do at this moment. So for now we can just do something like that. Yeah, anyway, Graham, good point about the address, CFG num. Okay, so we need to do those setup packets, and I guess we'll take care of that for the next time. One more thing I probably want to do, private device configured. So whenever we reset the device, we also, maybe we can do it here. Whenever we reset, we also take a note that it's not configured, and then here, if it's not configured, then only then we set device configuration. We don't want to always send it whenever it acknowledges a packet. Otherwise, it will send the device configuration, it will acknowledge it, and then we'll send it again over and over, and we definitely don't want that to do. So yeah, so for the next, so we went pretty, I think we can probably commit this as a work in progress. Yeah, just those two, I guess. Maybe we can also commit this, yeah, emulator demo project. We can also commit this later as a separate, I mean, it's probably useful for people who wants to debug the emulator like we did in Visual Studio Code, so why not? So let's quickly review what we did here. We added a USB controller, with this DPRAM start address, and then we made this a bit more readable by changing those numbers to KB and MB, and created the USB controller and also the USB DPRAM, which we haven't used but we will use next time. And then yeah, we remove this comment. This should have been a part of the previous commit, but whatever, never mind. And then we also created this USB, which it already starts interacting with the simulated code. It can send this reset condition, and next week we'll probably have reset and set device address, and then I think we won't have a lot of work to do until we can get the serial USB, the USB CDC output, and then we'll be happy. We'll have a functional serial USB, and we can probably then extend this to provide more comprehensive interface for interacting with the USB in the emulated code. So fit USB initial USB implementation not functional at this stage, only resets the device once it enables USB. Then USB peripheral. Next up, send that was a set address, right? Set device address, setup packet, send set device configuration setup packet, and then probably implement serial over USB CDC. And for the next time, let's take a note. There was this method that process control request, right? With all those different control requests, like process control request. Is there only one? Yes. C process in usbd.c. So just a note for future self for the next time. Okay, and then we committed, and then we can also add here just sure add debug configuration for VS Code. Great. We don't really need this UF2, and let's keep these notes here for the next week. And yeah, I'm pretty happy with the progress we had this time. As always, I hoped we could like close the loop in this session, but at least we fixed. I mean, we implemented the basics of the USB peripheral, and we figured out all the roadblocks, such as this interrupt issue and that piece of code that we left from the past that disables writing to the USB. I loved seeing Graham's comments on the chat. It was really useful. Thank you for joining, and thank you also all the other friends. We had like Steve and Valerio, Tomasz, and also Francisco and Nekari. So you are pretty much regulars now. That's great to see you every time. And yeah, I will see you again next week. Next Tuesday, we'll keep working and making this USB peripheral. I hope so. Work and speed all those debug messages from the programs at us, and then maybe we can even take a look at CircuitPython. I don't know. As always, I'm super optimistic. So we'll see next week. So until then, have a great week, and see you again next week. Bye bye.